Educator.com, we're going to be discussing dividing monomials. The first property of exponents is if m and n are integers and a is a non-zero number, then if you are dividing monomials with the same base, then you subtract the exponents. Recall that when we talked about multiplication, if you're going to multiply expressions with the same base, then you add the exponents. Here we're dealing with division, so we're going to subtract the exponents. And notice there's a restriction that a is a non-zero number because it is not allowed to divide by 0. That would result in an undefined expression. Here's an example. X to the 6 divided by x squared equals x, so these have the same base, therefore subtract the exponents. This is x to the 6 minus 2, or x to the 4. Thinking this out a little bit, what allows us to do this? Let's approach this a slightly different way. Well, you know that a number raised to a power means that I'm multiplying that number or variable times itself by 6 times in this case. So that means I have x times x times x 6 times. Okay. In the denominator, I have x times x. So if I simplify this, I'm going to cancel out 2 of the x's, and that's going to leave me with x times x times x times x, or x to the 4th. Again, these rules, such as the ones taught in the lesson about multiplying monomials, allow you to do operations more quickly, more efficiently. But the underlying logic comes from this. But if you just recall this rule, you'll quickly be able to divide monomials with like bases. Okay, if m is an integer and a and b are numbers and b does not equal 0, then if we have a quotient raised to a power, we can break it out so that we can apply this power to the numerator and here to the expression in the denominator. So again, we are not allowing the denominator to be equal to 0 because that would result in an undefined expression. Looking at this with an example, x divided by y cubed equals x cubed divided by y cubed. Thinking this out a little bit, if I have x divided by y cubed, it's telling me that I'm multiplying this expression times itself 3 times. So that's x divided by y over y times x over y. So that's 3 times. Writing this a slightly different way, it's x times x times x over y times y times y, which is x cubed, y cubed. Again, another rule that makes sense. These two are really equivalent. You end up with something equivalent, but by knowing the rule, I can just go straight from this to this. This one is a little bit more conceptually difficult, but what you just need to remember is that if a is a non-zero number, then a to the 0 equals 1. So anytime you have a number or variable raised to the 0 power, that's simply equal to 1. For example, if I have 5 raised to the 0 power, that's 1. If I have x to 0, it's 1. Now, why is this? Well, think about it this way. If I have x raised to any number where n is an integer, and I have that same thing, and I'm dividing. According to the rule we just learned a bit earlier, I would approach this by saying x to to the n minus n. So I would subtract the exponents because this has the same base. And what that's going to give me is x to the 0. Okay. Well, looking at this slightly differently, x to the n divided by x to the n, well, these are the same. They're going to cancel out. So I'm going to get 1. Well, if x to the n over x to the n equals x to the 0, and x to the n over x to the n equals 1, then in order for all of this to work and be logical, x to the 0 must be equivalent to 1. So that's the background for why we define a to the 0 as being 1. The final property we're going to discuss talks about negative exponents. If n is an integer and a is a non-zero number, so we have that restriction because we're dealing with division, then a to the negative n equals 1 over a to the n. Let's look at an example using this. If I have x to the 2 over x to the 4, remember that the way I'm going to handle this is to say x to the 2 minus 4, because these have the same base. I'm dividing exponential expressions with the same base. So that's going to give me x to the negative 2. Okay, now why is this going to be equivalent to this? Well, looking at this slightly differently. X squared over x to the 4th, I multiply this out, and what I really have is x times x divided by x times x times x times x. Okay, x's cancel out. That cancels, and that's going to give me 1 over x times x, or 1 over x squared. So again, in order for this to hold true, and my rule about dividing exponential expressions with like bases to hold true, this has to be equal to this. Because this rule told me I'm going to end up with x to the negative 2. And then I have another rule that I'm using mathematically that's telling me that we'll end up with 1 over x squared. So these two must be equivalent. We say that these two are equivalent. Okay, we've learned 4 properties today, and now we're going to apply them to examples. In this first example, I'm going to have to use my rule for dividing expressions with exponents when I have like bases. Remember, for example, I said that x over x to the 6th divided by x squared would be equal to x to the 6th minus 2, or x to the 4th. So I'm going to apply the same rule just to a slightly more complex expression. Well, I have 27 over 18, and that's just going to simplify to 3 halves. So 27 divided by 18 is 3 halves. And then I'm going to have x to the 4th minus 2. Y to the 7th minus 4. And then z to the 9th minus 6. Okay, just doing my subtraction is going to give me 3 halves x squared, y to the 3rd, z to the 3rd. So again, I simply applied my rule that allows me to divide expressions with the same base by subtracting the exponents. And this is in simplified form because my bases are present only once. I did simplify my fraction, and I don't have any powers raised to powers. Example 2 is slightly more complex because I have a quotient raised to a power this time. What I'm going to do is first simplify what I have inside the parentheses before dealing with raising that all to the 3rd power. And I'm going to approach this by remembering that a to the m divided by a to the n, my rule tells me that if I have the same base and I'm dividing, I subtract the exponents. So looking inside the parentheses, what I have is 3 divided by 15. So that is, of course, 1/5. X to the 4 divided by x to the 3, they have the same base, so I'm subtracting. For y, I have y to the 6th minus 2. And then I have z squared, but I'm going to stop and notice something. I have to apply a second rule. Recall that a number to the 0 power is 1. Therefore, z to the 0, in this case, is 1. So instead of, if I subtracted z to the 2 minus 0, it would just be z squared anyways, but I just want to realize that this actually equals 1, and I'm going to put it down as that. And I have to remember that I'm raising this all to the 3rd power. Okay, the second thing I want to do is get rid of the parentheses by applying my rule that tells me if I have a quotient raised to a power, it's equivalent to this expression. So I'm going to take care of that next. So let me go ahead and subtract to finish this out. That's x times y to the 4th, 6 minus 2 is 4, and then z squared over 5. Okay, and I can actually just eliminate this 1 as well. Now I'm applying my rule. This tells me that what I have is the top, x, y to the 4th, z squared, all raised to the 3rd power. In the denominator, I have 5 to the 3rd power. Remember that my rule for taking a power to a power is to multiply the exponents. So if I'm going to multiply the exponents, that's going to give me, this is really x to the 1 if you think about it that way. So 1 times 3 is x to the 3rd, y to the 4th times 3, that is y to the 4th raised to the 3rd power, raised to the 3rd power, that gives me y to the 12th, z to the 3rd raised to the 3rd power is 3 times 3, that's z to the 9th, actually that's a z squared, z to the 6th. Okay. So to clarify, it was z squared here. Okay, so now I have 5 times 5 is 25 times 5 is 125. And this gives me my expression in a simplified form, because I no longer have powers raised to powers or bases that are repeated. I've also simplified my fraction. When I started out, I took care of simplifying what I could within the parentheses, and that required that I applied 2 rules. I had to divide expressions that had the same base by subtracting the exponents. I also recognized that z to the 0 power is 1. Once I did that, I ended up with this, and then I applied my second rule about a power raised to a power, and that gave me this numerator to the 3rd power divided by the denominator to the 3rd power. In order to get rid of this, I multiplied my exponents, since this is a power raised to a power. And that gave me x to the 3rd, y to the 12th, z to the 6th, all divided by 125. So that is simplified form. Okay, in this 3rd example, I see that I have some negative exponents. And part of simplifying is to get rid of those. Although I'm not going to do that quite yet. The first thing I'm going to do is proceed as usual, dividing by subtracting exponents when I have like bases. So first for p, and I have to be really careful because I've got negatives and I'm subtracting. I have to make sure I keep my signs straight and correct. So this is p to the negative 2 minus 4. Okay, so I divided these. Next I'm going to divide the q's. That's q to the 3rd minus negative 3. Now r's, I have negative 4 minus negative 2. And in the bottom, I have s to the 0, which we'll talk about in just a second. So I'm going to proceed and do my subtraction. Negative 2 minus 4 is p to the negative 6. Q, and this is 3 minus a negative 3. That becomes a positive 3. So that's 3 plus 3 is 6. And it's very easy to make a small mistake like this when you're dealing with negative and a negative. So it's 3 plus 3, which is q to the 6. And then again, I have a negative minus a negative and then a negative 2. So that's minus 4 plus 2. And that's going to give me r to the negative 2. That's going to give me r to the negative 2. Okay. Let's look at this bottom. I have s to the 0 equals 1. Recall the rule that tells me that any number raised to the 0 power is 1. So on the bottom, I just have 1. Now, thinking about the rule that tells me that if I have a negative exponent, so a is raised to the negative n, that is equivalent to the reciprocal of that base, so 1 over a, converting the negative n to a positive. So a to the negative n is equal to 1 over a to the n. This is not in simplified form until I get rid of these negative exponents. So looking at this one piece at a time, that tells me that p to the negative 6 equals 1 over p to the 6th. Okay, so I'm going to put p to the 6 down here. Q is already, it has a positive exponent, so that's easy. I'm just going to put that up here. R is also to a negative power. So r to the negative 2, according to this rule right here, is 1 over r squared. Therefore, I need to move the r to the denominator, and I need to make the negative 2 positive. So my simplified form is q to the 6th divided by p to the 6th r squared. So the way I handled this to get rid of these negative exponents was to first just do the division. Divide terms with like bases so that I'm not working with as many terms. That gave me p to the negative 6, q to the 6th, r to the negative 2. The next thing I wanted to do is rid myself of these negative exponents by applying this rule. And I took the reciprocal of these, and then I made the exponents positive to get my simplified form. Okay, in our fourth example, we have a lot going on because we have negative exponents, we have a powers raised to powers, and division. Remember, when you're approaching these, first simplify what's inside the parentheses. And I'm going to do that by using my rule for dividing. And I have the same bases, c, 2 d's, and 2 e's, so I'm going to just subtract the exponents to divide those terms. Starting out, I have 2/3, c to the negative 3 minus 4. Then I have d squared minus negative 3, e to the 4th minus negative 6, e to the 4th minus negative 6. All of this is raised to the negative 3rd power. Then I'm just going to do my subtraction. Minus 3 minus 4, c to the negative 7. Here I have 2 minus negative 3, so that 3 becomes a positive. I have 2 plus 3, d to the 5th. And then e, 4 minus negative 6, that becomes a plus 6, a positive, so it's 4 plus 6 is 10. Okay, now all this is it's negative 3rd. Before I go on and deal with this power raised to a power, I want to take care of the negative 7. I want to avoid having negative exponents. And I can just remember my rule that says that a to the negative n equals 1 over a to the n. So if I have a c to the negative 7th, I can just change that to the reciprocal and change this negative 7 to a positive. So this c is going to go to the denominator and become c to the 7th, d to the 5th, e to the 10th. Now I'm ready to work with this negative 3. my rule about powers raised to powers, a quotient raised to this power, tells me that I have a to the m over b to the m. Okay, so I'm going to apply this -3 to both the numerator and the denominator. That's going to give me 2d to the 5th, e to the 10th, -3, 3, c to the 7th, also to the -3. Since I have powers raised to powers, I need to multiply the exponents. So I'm going to go up here and continue on right here. It's going to give me 2 to the -3, 5 times -3 is going to be d to the -15, and then I've got e to the 10th raised to the -3. I multiply 10 times -3 and get e to the -30th power. In the denominator, I've got 3 to the -3, and then I have c to the 7th to the -3. So then in order to take this power to the power, I just multiply 7 times -3 to get c to the -21. Okay, what I want to do now is get rid of, I have all these negative exponents, and what I'm going to do is take the reciprocal of each of them and change the exponents to positives. Therefore, the 2 to the -3 is going to move into the denominator and become 2 to the 3rd. That's going to give me d to the 15, e to the 30th. So I moved all these three into the denominator and made their exponents positive. In the denominator, I have 3 to the -3. That's going to go up to the numerator, and then c to the 21. I'm almost done. Part of simplifying, though, is making the fractions simple. So when I simplify this, I'm going to end up with 3 times 3 times 3 is 27. C to the 21. 2 times 2 is 4. Times 2 is 8. D to the 15th. E to the 30th. So this is my simplified form. And that was actually a pretty complicated problem. Remember, when you see something like this, start out by making what you have inside the parentheses as simple as possible before you work with what's outside the parentheses. So in working with this, I did my division of all the exponential expressions with the same base, and I came up with this. I looked at it and realized, well, I have a negative exponent, so I used my rule that allows me to convert that to from c to the -7th in the numerator. Instead, I will have c to the +7 in the denominator. So that's 1 over c to the 7th. Once I had that, I applied my exponent -3. All of this is being raised to the -3rd power. I applied that to the numerator and to the denominator. Multiplied the exponents to give me this. And my final step was really to convert this, all of these, into terms with positive exponents by taking the reciprocal and making those exponents positive. And then I just took care of my constant. Okay, that concludes this lesson of Educator.com. I'll see you next time.